Chapter 1, Lecture 1, Introduction to Basic Concepts. So what is thermodynamics? This chapter lays out some very basic nomenclature or definitions and terms that we will need to be familiar with throughout the semester. Thermodynamics is the science of energy. So what is energy? Energy is the ability to cause changes. The name thermodynamics stems from the Greek words thermi, which means heat, and dynamos, which is power. So thermodynamics you can think of is energy flow, heat flow from one object to another object. There are two laws of thermodynamics. The first law of thermodynamics is really an expression of the conservation of energy that we saw back in university physics. The first law asserts that energy is a thermodynamic property and that it is conserved. The second law of thermo asserts that energy has a quality as well as a quantity, and actual processes occur in the direction of decreasing quality of energy. Now, this is kind of a very confusing concept for a lot of students, but what the second law of thermodynamics means is that energy flows in certain directions, preferably. For example, here shows a rock on top of a hill. If you just sort of push the rock off, it falls down to the bottom. Well, that conserves energy. It converts potential energy at the top of the hill to kinetic energy at the bottom of the hill. But you don't see rocks by themselves sort of jump up, from the bottom all the way to the top. I mean, you would still conserve energy, but that kind of process just doesn't happen by itself because, there's a definite, lowest energy level that things prefer. There's no joke that I remember my thermodynamics professor telling me is that, you can't unscramble an egg. Once an egg is scrambled, you can't put it back in the egg and undo it, right? So that's sort of what the second law of thermodynamics says, is that it places a limit on the direction that certain processes can go. So there's more to it than just conserving energy. Obviously you have to conserve energy in any kind of process, but just because you conserve energy doesn't mean that process is going to occur naturally. And the reason it doesn't is according to the second law of thermodynamics. So there's a lot of areas of and applications of thermodynamics, from your typical, household heat exchangers, hot water tank, to commercial aviation, to power plant generation, heating and air conditioning systems, automobile engines. We'll take a look at all of these as we go through the semester. So every textbook I ever read and ever taught out of, the first chapter always has a section on units, dimensions, and significant figures, and this one is no different. And so, I'll let you read over these definitions from the book, and obviously, we will be using both metric and English systems, which may be sort of new to you if you've only had physics course. We tend to stick with the metric system, but engineering classes you have to use both because in the real world both systems are used. So if you're not familiar, if it's been a while since you've covered the metric and English systems, just kind of read over that section in the textbook. So what is a system? A system is a quantity of matter or a region in space chosen for study. So a system is usually what we're interested in studying. For example, it may be an air compressor, or it may be a water heater. That's the system. Everything outside the system is known as the surroundings. And between the system and the surroundings is the boundary. Now this boundary can be real or imaginary. It depends on the particular problem at hand. The boundary can also be movable or fixed. So we'll take a look at a lot of those throughout the semester. There's Two kinds of other things we worry about is what's known as a closed system or an open system. A closed system is defined such that no mass transfers across the boundary. However, energy can transfer across the boundary. On the other hand, an open system allows both mass and energy to transfer across the boundary. And a very good example is shown on the page here. For example, your conventional water heater. You have cold water coming in and hot water coming out. So a lot of times in our study of thermodynamic systems, we're not going to keep track of individual particles flowing. So what we do is we establish what's known as the control volume. And we keep track of what comes into the control volume and what goes out the control volume. Now the control volume is just our boundaries that separates our system from the outside world. In the figure here, we have a conventional nozzle. That's also another example of an open system, because you have obviously mass and energy coming in and out here. And you also have a case of where you have a piston, like an auto cycle, the automobile engine, where you have mass coming in and the boundary physically being able to move up and down. So this is the top one here is like a movable boundary. This top will actually physically move up and down. Properties of a system. So a property is any characteristic of a system that you can use to classify it. So for example, mass, volume, temperature, pressure, density are all properties of a system. We distinguish two types of properties, either intensive or extensive. So intensive properties are those that are independent of the mass. So there would be things such as temperature, pressure, and density. Extensive properties are those values that depends on the size or the extent of the system. They depend on the mass, in other words. Extensive. Specific properties are extensive properties per unit mass. Specific properties. So the little diagram here shows you, for example, all of these guys at the top here are properties. And we sort of can divide these up into the extensive ones, whose value depends on the mass, and the intensive ones where they do not depend on the mass. Continuum. This is another topic the book talks about it. And again, we won't see this a whole lot, but it'll come up every now and then throughout the semester. We're not going to treat fluids and gases as individual particles. We know that matter is made up of all these atoms, yet it's very convenient to disregard the particle nature and treat them as like a homogeneous mixture. This continuum process allows us to treat properties as point functions and assume the properties vary continually with no jump in discontinuity. So in other words, what that means is that in a region of space, if we have a fluid, we're going to treat everything in the fluid that have the same density, for example. Where in reality, on a microscopic level, you might have more particles in one area than another area. So this is pretty much the case throughout the semester, that we'll treat fluids and gases as a continuum rather than individualized particles. So here's some very basic definitions of that we'll deal with throughout the semester as well. We need to understand what density is, mass divided by volume. So the unit here in the metric system is the kilogram per cubic meter. Specific volume is the inverse of density. Notice also it's very easy to confuse the small v here with a big V. So just be very careful about that in the book. This big V is volume and the small v is the volume per unit mass. Specific gravity, ratio of the density of substance to the density of water. This is very useful to allow us to compare different fluids with water. So for example, if you look in this table, for example, if you look at mercury, for example, mercury has a specific gravity of 13.6, which means it's, that's why when, if you have a beaker of mercury, it's going to feel a lot heavier than if you have the same beaker filled with water. It just gives us an intuitive feel for the substance. The last property is specific weight, which is defined to be the density times the acceleration due to gravity, g. And the units is newtons per cubic meter. So thermodynamics deals with what's known as equilibrium state. So what's an equilibrium? It's a state of balance. So in an equilibrium state, there are no unbalanced potentials or driving forces within the system. So we can further break that up into several different kinds of equilibrium. There's thermal equilibrium, mechanical equilibrium, phase equilibrium, and chemical equilibrium. This is kind of useful for us because that's sort of what how we do how we look at the systems. So for example, if you have a state one where you have a certain mass, temperature, and volume, and let's say we're going to take this piston and we're going to move it upward to go to state two. So we're going to increase the volume, for example. Well, what we're going to do is we're not going to worry about the transition from state one to state two. What we're going to do is we're going to look at the parameters in state one. We're going to move the piston up. We're going to let everything settle down, and then we're going to measure our properties. Because the problem is that interim where you're moving the piston becomes very complicated. For example, you get temperatures moving around, adjusting everywhere. It's not uniform, for example. So we're going to let it stabilize a little bit, and then we're going to wait till it stabilizes, and then take our reading. This actually simplifies the problem, so we don't have to worry about that very complicated interim process that you're going between a couple of states. The state postulate. Our book states the state postulate in chapter 1, but it doesn't actually become really relevant to us to later chapters. But what the state postulate says is that the state of a simple compressed system is completely specified by two independent intensive properties. So first of all, this builds back on what is an intensive property. Remember, intensive properties do not involve mass. So you need two of those kind of intensive properties to completely specify a system. It doesn't matter which ones they are, but you do need two of them. One's not enough. So here's an example of nitrogen at a temperature of 25 degrees C and a specific volume of 0.9 cubic meters per kilogram. So these are both intensive properties. There's two of them. So this state is completely specified, completely fixed. Processes and cycles. So a process is a change in a system that undergoes from one state to another state. So one equilibrium state to another equilibrium state. The path is the series of states through which the system passes during this process. So oftentimes what we will do is we will graph property A versus property B, and we'll indicate a state, the initial state of the system, let's say it's state 1. We'll indicate the final state of the system, like state 2, and the process is the path it takes to go from state 1 to state 2. How does it get there? And we'll find there's different ways to get there. And I'll show you that in a subsequent slide. So here's a very good example. So here we have an initial state, we have a final state, we have the process path going from state 1 to state 2. This is a simple system where we start here at 1, where we have the gas. Let's say we have a gas in here. We compress the gas by applying a force down to state 2, which is obviously at a smaller volume, right? So we're going from volume 1 to volume 2. The pressure is going to increase. So we'll go from pressure 1 up to pressure 2. The pressure at 2 is higher than the pressure at 1. So this completely specifies the system, how it changed. Now there's different ways you can get from state 1 to state 2. This process is pretty general, but what would happen if you had a isothermal process? So in that kind of situation, you would fix the temperature. The temperature at 1 is the same as the temperature at 2. Another kind of process is what's known as an isobaric process, a process during which the pressure remains constant. Now, obviously, this is what would that look like on this chart? If the pressure remained constant, you would go from here, for example, straight across to over here, right? Because that way we would keep the pressure constant to whatever this pressure was there. That's how you would indicate an isobaric process on this pressure versus volume diagram. Another way you could do what's known as a isochloric process, where you keep the volume constant. So what would that look like on a chart like this? You would go from like here up to there, right? For example, state 1 to state 2 up here. That would be an isobaric process because the volume would stay constant. You would stay at V1, going from state 1 to state 2. And of course, you can always go from, like, let's say you wanted to go up from 1 to 2, but you went along this kind of path. Let's say we go this way over to here, straight across till we get to this point here, and then we go up the chart up to this way. So we go this way first, then we go up this way, right? So the process where at the horizontal part, this part here would be we keep the pressure constant. That would be an isobaric process, and this process from here up to there, we keep the volume constant. That's an isochloric process, right? So what I'm saying is there's different ways to get from point 1 to point 2 than rather go the direct path. Steady flow processes. So the term steady implies no change with time. The opposite, of course, is unsteady or transient. So a large number of engineering devices operate for long periods of time under the same conditions. They're those known as steady flow devices. So during a steady flow device, the fluid properties when the control volume change with position but not with time. That's the key factor. So some steady flow devices are turbines, pumps, boilers, condensers, heat exchangers, or power plants, or refrigeration systems. So under ideal, approximations, which is what we're going to do, all the kind of interesting systems that we're going to talk about are what's known as steady flow devices. So thermodynamics and the zeroth law of thermo. So the zeroth law of thermo says that if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. Which sort of, is kind of, in a way, common sense in a way. So by replacing the third body with a thermometer, the zeroth law can be restated as follows. Two bodies are in thermal equilibrium if both have the same temperature reading, even though they are not in contact. So here's two bodies here, we at different temperatures. If we bring them in contact and then they stabilize at the same temperature, then these two objects, the iron and the copper, are in thermal equilibrium.